Yeah, g'day, Mark here, and welcome back to my channel. Now, I've spent a couple of years modernizing this early 1980s Schaublin 125 CNC lathe, converting it over to LinuxCNC. It's a very beautifully constructed precision lathe, not terribly large, but just the right size for my home shop. Now, I got it in very, very nice mechanical condition with almost no wear, but it was brain dead. So I've had to do a lot of work to convert it over, and I'd really like to finish that CNC conversion. I've been using it for a while, but the one area I still need to really address is bringing the whole spindle control under LinuxCNC's authority. So what's the problem, you might be wondering? LinuxCNC's been able to control spindles forever. Within a CNC machine, you usually use the S word for spindle speed, and you just command whatever you want. Speed 400, speed 800, whatever your machine's capable of. That's at least in the G97 mode, which is just ordering an RPM. There's a second mode typically used on lathes called G96, where instead of specifying the RPM you want, you specify how fast you want the tool to be passing over the surface of the work. So let's say for carbide and steel, you want a surface speed of 150 meters per minute. And then the controller will do the maths to work out, depending on radius of the part, what RPM you need to give you that surface speed. Now, as a prerequisite for using constant surface speed or just commanding an RPM that I want, I obviously need closed loop spindle control so that when I order a speed, it can set the whole drive system as necessary to actually meet and maintain that speed. Now, the most modern CNC machines, that's super easy. They just turn the spindle itself into a huge motor. So it's got a big servo motor onto the main spindle, and they just drive that servo. There are also machines that have a big servo motor with a belt drive onto the spindle, but it's basically the same concept. The Schaublin 125 CNC, this was their generation 1 of doing a CNC conversion. So of course what they did was take their best manual machine and all its best features and just automate some of them. So in this case, the drive system has been taken over almost entirely from the manual machine. And that leads to a bit of excessive complexity. So there was a big 3-phase motor, which was a Darlander motor, which means it's got 2 ways of connecting the winding. I think the speeds were 4-pole, so 1500 RPM, or 8-pole, which is 375. Does that sound correct? I'm not sure. After that motor, you've got a constant velocity transmission. It's just a mechanical one where this big wheel on the front was used to squish the sheaths of a pulley together or apart. And if you squish the bottom sheath together, then the belt would run out on a larger radius at the bottom, and the top sheath was only spring-loaded together and it would follow. So if the bottom sheath expanded on its radius, then the upper one would move to a smaller radius, and therefore you get a lower reduction ratio. Now, following this constant velocity drive is a gearbox, and it's basically a classic lathe back gear. It's either going to run in 1-to-1 mode, where the input shaft speed is the same as the output shaft speed, or 6.5-to-1, giving you a massive reduction in speed and a huge increase in torque. Then from there, you've simply got a big tooth belt drive up to the spindle itself. Now, the only significant change Schaublin made on this first generation CNC machine was to remove the big mechanical hand wheel, which adjusted the pressure on the lower sheath of the constant velocity transmission, and replace that with a small 3-phase motor driving through a worm gear to do that same mechanical setting of that preload. So let me draw up a quick block diagram and try and explain what I'm trying to achieve with software here and why this is quite a difficult challenge. So the brains of the whole thing is just a normal PC running LinuxCNC. It has a bunch of Mesa cards that do I/O control. None of this wiring I've had to adjust. I've had all of this done so far, but I just haven't had any logic to control it all. So what I've been doing so far is simply running the VFD open loop. I'm giving it a 0 to 10 volt speed control, left, right, brake. Oh, I forgot the gearbox. All right, let's just glue on a bit of repair paper. So the physical interfaces I've put here on my control panel are spindle start and stop buttons, a spindle speed override encoder. I've got variator bias slower, bias faster spindle speeds, and then a backgear select. So all of this information is fed back from the control panel to LinuxCNC via Mesa cards. Let's ignore this bit for a minute. As long as the gearbox and the constant velocity transmission are not being altered, you've just got your standard VFD controlling a motor, controlling a spindle with encoder feedback. Okay, so that would be a simple closed loop system. You drive the VFD to a specific spindle speed using a PID feedback loop based on encoder's reported speed and bias that VFD until you get the speed you want. So that would be pretty simple, and that is in fact what Schaublin then did on the follow-on model of this lathe called the 125 CCN. They dumped the back gear, they dumped the constant velocity transmission, and they just put in a big ass spindle motor here and run it closed loop off the spindle. I've had a lot of suggestions that that's what I should do. Just rip all this stuff out and put in a big motor. But I already own these bits. I'd have to pay money to rip it out and change it. It would mean buying a big motor, a big VFD, and then making a whole bunch of mechanical parts to make the thing fit. The second issue I have with ripping it all out is the advantage of mechanical speed reduction is that you get an equivalent increase in torque. While this is a little lathe, but I don't need all the torque this thing can generate, this thing can generate more grunt than a rutting sperm whale. So the two reasons for not replacing all this is one, it gives me massive torque when needed, and two, it's already there. And changing it would be work and effort, and I'm kind of allergic to work and effort. So let's stick with what we've got and see if we can make it work. The gearbox control is probably the easiest. The gearbox, I thought, could only be switched when the spindle is stationary. However, looking at the gearbox used on the manual, it can be changed while running. However, because the speed change is so dramatic from direct drive to a 6.5 to 1 reduction, you certainly wouldn't want to be activating this back gear to shift while you're in a cut. This is the easiest part of the logic. We'll just decide before starting the spindle, based on the initial speed command, if we're above 400 RPM, let's go for high gear. And if we're below 400 RPM, let's go for back gear. There's no feedback of position from that gearbox. So we can only infer gearbox position by starting the spindle and looking at the overall reduction ratio. It gets difficult because the change in inertia from lowest ratio here plus lowest ratio there versus highest ratio here and highest ratio there is a huge change in inertia. If you tried to do all the control with single proportional integral values, you'd end up either with oscillations at one side or with extremely slow performance at the other. And I don't really want either. So what have I done here? Since I first got the lathe working, I've just been using back gear manually, push the button, change the back gear. I've been manually biasing my constant velocity drive either towards higher speeds or towards lower speeds. The ratios are of course opposite, higher speed, lower ratio, but whenever I say high, I'm talking about high spindle speeds. I'm trying to keep that consistent throughout everything. Unfortunately, this three-phase motor, which turns at constant speed, driving some gearing to squeeze it together or open it. It takes about 5 seconds to go from the lowest possible ratio to the highest possible ratio. However, the change in reduction ratio is not linear over those 5 seconds. Now, there were a bunch of recommendations that I add some form of feedback here, maybe like a linear encoder or something, to feedback what is the real constant velocity transmission ratio back into the system, because then I would know all the time what the ratio is. Then it would be easier to assign the appropriate gain to the appropriate reduction ratio or inertia. But once again, adding something here is not trivial. It requires pulling it all apart, scratching my head, working out where I could put a little linear encoder on here or rotary encoder, and making that whole system work. So my first attempt will be to try and get this to work without any feedback from the CVT. It does have limit switches, but those are only used as inhibits to the CVT. They're not fed back into the Mesa card, and therefore LinuxCNC doesn't know they exist. So what's the software going to need to make it all work? Well, to make the VFD control the speed loop, it's going to need to have closed loop control, isn't it? But because we're going to have massively variable inertia, we're going to need some form of a variable gain staging. To be able to work out which gain to use, we're going to need to know the reduction ratio. So somehow we're going to need to infer the reduction ratio. We're going to need to define speed range. What I've already found is that if I have the CVT, it's giving its highest speeds, and I run the motor at the highest speed in Gearbox high ratio, the spindle can reach mechanically about 4,200 RPM. If I run 10 Hertz, most reduced CVT and back gear, I get something like 36 RPM. However, this value I can't use. And the reason for that is I think it's the collet closer. The maximum speed for the big pneumatic collet closer is only 3,000 RPM. So I need to limit that speed to not above the 3,000. On the follow-on version of this lathe, Schaublin switched from a large single piston to a double small piston collet closer and up the RPM to 4,000. Ideally, I just want the LinuxCNC to take a speed command, S2000 RPM, and the system automatically set the spindle to that speed at the most optimum motor RPM. I'm going to want some form of motor speed optimization so that we're biasing the system. Where possible, it's best to run that motor at 50 Hertz or thereabouts. We can give that some sort of a band, maybe plus minus 5 Hertz. And there's obviously some parts of the speed range where you're going to be beyond that. At the slowest possible speeds, you're going to drop down and eventually get down to the 10 Hertz minimum. And at some of the higher speeds will be up around the 70 Hertz. But where possible, it should try to aim to optimize the motor speed at around net frequency speed. The CVT can only be bumped with spindle running. You can't drive one of these things when it's stationary, it just damages the belt. I don't think this motor has a high duty cycle. So limiting the amount of CVT bumping it does would mean a wider acceptable frequency for the speed optimization. The big challenge we have here is how do we work out the reduction ratio? On the one hand, speed out is easy, right? Because we've got an encoder on the spindle, and I think it's an 8,000 count encoder in quadrature. So we have a very accurate measurement of output speed at all times. But to infer the overall ratio, we also need to know what's our input speed. And unfortunately, there's no encoder on the motor. Now, theoretically, I could add one, but we're trying to see if we can do all this with just software. What we do have is motor commanded speed. Between the encoder output and the motor's commanded speed, we can infer the overall gear reduction. However, The problem here is that this value is not actually motor speed, it's what we're commanding. So on the one hand, we'd be trying to control off a variable that we're constantly changing, and that's probably going to lead us to some pretty major dynamic issues and limits in this whole system. For example, if the motor's running at 10 Hz and we command 70 Hz, that command signal will instantly go to 70 or its equivalent motor RPM, while the spindle's only just started accelerating. So you get this very skewed, instantaneous gear ratio. I checked the VFD manual and it can output the motor's actual analog frequency as a 10-bit signal, 0 to 10 volts. I'm not sure if the VFD would scale my set limits 10 to 70 Hertz into 0 to 10 volts or truncate it. But the input resolution of the Mesa I/O card is 0 to 36 volts, 8 bits. So the VFD signal would only populate about 1/3 of full scale, and maybe even less if it's not scaling the limits. Now, since this is going to be a dirty signal and at some points be unusable, what we're probably going to have to do is switch between open loop and closed loop throughout the control regime. For example, when we're commanding the CVT and this ratio is constantly changing, it might be a good idea just to freeze the ratio, use some sort of an estimate or last commanded value, and then once the CVEs finish shifting, then we can switch back from open loop to closed loop. Another time we're going to need this is startup. When we first start the spindle, it has no idea what the gearbox's position is or what the ratio is. So it's probably a good idea on a first start at least to just start the motor at 10 Hertz. Give it a second or so for the motor speed to stabilize, and then do that initial calculation of what's my gear ratio. Because once you know the gear ratio, at that point you know your commanded spindle speed, you know your gear ratio, and you know your actual spindle speed. Now the system can then start working out what changes need to be done with the VFD and what changes need to be done with the CVT to actually produce that commanded speed. In my first attempt to program this, I used Chat GPT as an assistant with the code, and this is about as far as I got with it. I then end up in a sort of a purgatory of do A doesn't work, do B doesn't work. Hey, have you tried A? As you can hear from the speed changes, it's sort of right with following the constant surface speed velocities needed, but I have to freeze the ratio calculation so much of the time that you get these long pauses where the thing's recalculating, and then halfway through the cut you're accelerating again. We must be approaching a CVT bump somewhere around here. As the radius increased and I dropped down to the lowest ratio on the CVT and then the lowest frequency available, there was almost no torque left, so I did a manual stop and put it in back gear. I was also having some issues with the automatic switching of back gear at that point, so I also did this with just the G97 constant RPM mode, so all of the next cuts were done at 200 RPM. Now we need to go back up to high speed to cut the taper of the center of this part. I stayed in constant RPM mode for this because the test cut I'd done cutting air had the RPM wildly oscillating all over the place. At this point, the brake was also not activating again. I figured this wide trepanning tool would be a pretty decent torture test of the speed stability. Now the transition from trepanning at this smaller diameter out to do the balance weight dovetail clean out, the spindle speed didn't adjust fast enough and I stalled out. I guess what happened there is I didn't give it time for its speed change, so it needs time to slow back down. This is about where I gave up on Chat GPT and switched over to Claude AI to help me program it. And that was a big step backwards. After another week of mucking around with that, this is what it looks like. Regardless which speed I start at, it always starts at 10 Hertz up here. After about a second, it will have calculated the gear ratio. And based on that, it'll do a logic check. Am I on high range or low range? And is that correct for the commanded speed? The cutoff being 400 RPM. If it's got the wrong gear, it'll fault out. But otherwise it'll then start the spindle and try and accelerate with the VFD up to the target speed. And once it gets to that speed or gets to the maximum frequency of 70, it'll then look at adjusting the CVT to try and bring the motor RPM to 50 Hertz. Let's have a look. That PID performance is very slow on this run. And it's given us a ratio of about 2.6 to 1. That's about right for the lowest ratio high gear. Let's up it to 1000. That supervisor ratio 8 froze. That's the overall reduction ratio. That number should definitely refresh after a CVT bump, which it didn't. Okay, the actual ratio was 1.4. So as you can see, my CVT ratio is locking out. Let's switch over to the data set we've got. So I'll just stop the data logging. Still, it's given us some. This is the log file from my last runs. I actually ran that for quite a long time. I filled up a card on my camera, so you only saw the second half of this. So first it's looking at, is that ratio filter frozen? Is it running? Is it saturated, etc.? Then we look at the whole PID map. All of this stuff was just automatically programmed by Claude. All I did was say, write logging software to give the data needed to diagnose the system. My first attempts were all based on me providing observed feedback into the AI, but having it data log like that, I can then just give it the file and let it diagnose itself, which theoretically should be better, but in practice hasn't made a big improvement. I'm getting a lot of very intelligent sounding analysis. So whatever was freezing that ratio calculation has now been removed. Still an unstable mess. Man, this still sucks. That's where I'm at with this whole controlling of the spindle thing. The model I tried to do with Chat GPT was a bit simpler, and I got it to the point where it was sort of working but not well enough. When I switched to Claude, we went straight for a more complex model because I guess I'd learned some stuff and understood it a bit better. Also got there to a point which was sort of usable but sort of not, as you could see in the test cuts I did. And unfortunately, using the free version of these softwares, you hit a limit of how long a thread can be, and then you have to start a new thread. And I started a new thread with all the knowledge that I'd gained. You still end up sort of stepping back a bit and heading off down some weird tangent. As long as I can command a spindle speed, have it set it and hold it stably, I'm actually already better off than I was before. Because before, like if I wanted 2000 RPM, I'd have to estimate roughly what gear ratio I had and then give it some fake number like 80 to give the correct output because the scaling was never right for any specific speed. If I can command a speed and it'll hold a speed, that's already an improvement. The challenge is to get it also usable with constant surface speed cuts and fast enough reacting that I don't end up having these big changes in speed and speed over and undershoots during a constant surface speed facing pass. However, I am rather losing confidence in this way of inferring motor speed through commanded speed and then trying to work out the gear ratio of it. I am wondering whether I'm going to be forced to bodge a spindle encoder onto the back of this motor as one way of getting better data to calculate that ratio from. What would you do? I'm sorry if this was an unsatisfactory video to watch. It was also a very unsatisfactory video to make. I've put a lot of hours into playing around with this, tried all sorts of different ideas, everything I could come up with, and the closest I've got to a solution, as long as I don't use constant surface speed mode, would be an improvement, but the whole idea of a lathe like this is to use constant surface speed mode. Sorry about that. Hopefully next time I'll get a more interesting video out for you. See you next time. Thanks for watching.